Good day, grade 8. I'm Miss Babo, and today's lesson will be about the effects of a current. In this section, we will be looking at the energy transfer that occurs in electrical systems, focusing specifically on what effect a current will have on certain devices. In this section, we are going to look at what the effects are of an electric current. So, an electric current can have the following effects on a device. Firstly, it has the ability to heat up a device. Secondly, it has the ability to form a magnet. And thirdly, it can cause a chemical change to take place in a circuit. So let's start with the heating effect of current. In a circuit, energy is transferred through the electric current. This means that the electrons that will move through certain devices like light bulbs or elements in kettles, heaters and geysers will bump against each other, and this causes the device to heat up or to become hot. So let's have a look at the heating effect in three different devices. Starting on the left hand side, we have a toaster. Our middle image is the element found at the bottom of a kettle or a heating urn, and on the right hand side we have our light bulb. Now, with all three of these, the current flows through these specific devices, and because of them all three having a high resistance, it will allow the electrical energy to be converted or transferred into heat energy. In all three of these, the electric current will pass through them, and the element that is found in the toaster, in the kettle, and in the light bulb has a very high resistance. Energy is then transferred to the particles that are found in the element that they can gain kinetic energy. And with that increase in kinetic energy, the temperature will increase as well. This will then allow these elements to heat up, to convert the electrical energy into light energy and heat energy, which will then allow these devices to work. Due to there being an increase in some electric devices, a fuse has to be placed into the circuit for safety reasons. A fuse is there to prevent any overheating from occurring in devices, as a current, as you can see, has a heating effect on devices. So, a fuse is a short wire with a very high resistance. This will cause it to become very hot very quickly, and a low melting point, which means it will melt very quickly if the temperature is too high. A fuse can be classed as a device that is placed in series to create an opening by melting when a current becomes too big. If there is no fuse in place, it could create a short circuit. This will then increase the flow of a charge and could lead to an increase in temperature, which could lead to an electric fire. So what a short circuit is, it happens when another easier path is accidentally made in an electric circuit. A short circuit could occur if the electric current takes a path that has a lower resistance. This increases the flow of a charge and could lead to an increase in temperature, which could cause an electric fire. So the wire in a fuse will melt if the temperature gets too high, which creates a short circuit. This over here represents what a short circuit is. Now we move on to the magnetic effect of a current. So, a current carrying conductor will have the ability to create a magnetic field around it, causing it to behave like a magnet. This principle is used to make an electromagnet. When we speak about a current carrying conductor, there are certain requirements which this current carrying conductor must meet in order for it to become an electromagnet. So let's have a look at these requirements. Firstly, let's start with what a magnetic field is. So a magnetic field is the space where a magnet of a ferromagnetic material experiences a force. There are three specific ferromagnetic materials which we use to make magnets, and that is iron, nickel, and cobalt. Ferromagnetic materials can experience an attraction or a repulsion force in a magnetic field. Now, when we speak about ferromagnetic materials, there are hard ferromagnetic materials and soft ferromagnetic materials. A hard ferromagnetic material will take long to become magnetized, and they are able to keep their magnetism for a long period of time. Permanent magnets are made of hard ferromagnetic materials. But soft ferromagnetic materials become magnetic very quickly, but they do not keep their magnetism for very long. And these are used to make temporary magnets. So let's start with what an electromagnet is. An electromagnet is a piece of metal that turns into a temporary magnet when insulated or covered or wound around in wire. These wires are wrapped around it and it contains an electric current that is coiled around it to allow the current to pass through. If the current flows, the material used or the metal used will become a magnet, and if there is no current flowing, it does not become magnetic. What's important to remember about the metal that is used is that the metal must be ferromagnetic when making an electromagnet. So we should either use iron, cobalt, or nickel to ensure that an electromagnet will be produced. When we make an electromagnet, there are certain things we can do to make the electromagnet stronger. First thing we could do is to add more coiled wire around the ferromagnetic material. This means that there will be a bigger surface area of the ferromagnetic material that will receive the current passing through. The next thing we could do, or another thing we could do, is to use a bigger current, so amplify the amount of current that is flowing through the conducting wires. Or last thing we could do is to use a harder ferromagnetic material. As mentioned previously, a harder ferromagnetic material will stay magnetized longer than a softer ferromagnetic material. With electromagnets, we need to be able to determine the polarity of an electromagnet. This means determining which side of our electromagnet will represent the south pole and which side will represent the north pole. Now, the first thing we need to have a look at is the direction of the current round the ends of the coiled wire. So, if we have a look at this diagram over here, our current flows from a positive side to a negative side. So the current is flowing up on this side of the magnet, of the ferromagnetic material, and down again. To determine what the polarity is, we use the right hand grip rule, which means you take your right hand and your fingers wind around the electromagnet, showing which way the direction flows, and the thumb of your right hand will determine which side the north pole is of our electromagnet. Now, where do we use electromagnets? Electromagnets are found in many devices that we may not even be aware of. You may never see electromagnets, but they often lie hidden in many electronic products which you use. For example, a doorbell. When you press the doorbell, the electric current creates a magnetic field that attracts the ringer, which is this part over here, to strike the bell when the doorbell rings. In other devices, it could be found in speakers, telephones, industrial lifters, magnetic trains, generators, or motors that we use in our daily lives. Our final effect of a current is the chemical effect. So, an electric current can be used to cause a chemical reaction in a solution. This occurs because the current will break down the compound as it flows through. A specific process like this is known as electrolysis. The process of electrolysis can be explained as when an electric current flows through a solution and breaks a compound into elements. If we go back to what a compound is, it is a substance made up of two or more elements that have chemically bonded or reacted with one another. So in this section, for electrolysis, we are taking a compound and allowing an electric current to flow through to break up that compound into the separate elements that make up the compound. So the terminology we are going to use in this section for electrolysis, we'll start at the top. The first one is an electrolyte. What an electrolyte is, it is the solution that a current will pass through in order to break the compound into elements. Electrodes, they are the poles that come from the battery that are placed in the electrolyte to allow the current to pass through the solution. The one electrode will be called the anode, and that attracts the negative ions, so we call it the positive pole, and the cathode will attract the positive ions, so it is counted as the negative pole. This diagram represents what electrolysis is. The blue liquid towards the bottom of the glass beaker is known as the electrolyte. Underneath the word electrolysis, here we have our battery or our power source. Connected to our battery or power source will be the anode and the cathode. The cathode is our negative pole, which will attract the positive ions, which can be represented over here. And the anode is our positive pole, which will attract the negative ions as represented over there. So let's have a look at the electrolysis of copper chloride. This is an experiment where we take copper chloride, we allow an electric current to flow through it to break up the compound of copper chloride. So our electrolyte, which is the solution in which the current will flow through, is called copper chloride. The apparatus we use here is a power source. Now, what's important for this one is that the electrodes which will allow the current to pass through are made of carbon. This is because carbon is the only non-metal that is able to conduct an electric current. At our anode, we will have a brown layer that will gather around the anode, which represents the copper of copper chloride. And at our cathode, there will be two significant signs to show that the chlorine has gathered there. One, there will be bubbles that are present, and towards the surface of the solution, the second sign will be that you would be able to smell what the chlorine is. Our formula for the electrolysis of copper chloride, our chemical formula is CuCl2, will give us copper and chlorine gas, and our word equation is copper chloride will give us copper and chlorine. The next experiment is the electrolysis of acidic water. Now, the electrolyte here is sulfuric acid mixed with distilled water. Distilled water is unable to conduct an electric current because it does not contain any electrons. But, for example, our tap water will be able to. In this experiment, we are using distilled water. Distilled water will be mixed with sulfuric acid. And now sulfuric acid is considered a catalyst. A catalyst will allow a reaction to take place, but does not undergo any permanent chemical change itself. So it is there to ensure that the chemical reaction takes place, but does not play a role in the chemical reaction at all. The apparatus which we use is a Van der Hoff voltmeter. Now in this one, what's important to remember, the electrodes are made of platinum. At our anode, we will have the gathering of oxygen gas, and at our cathode, there will be the gathering of hydrogen gas. The formula for this electrolysis equation or this electrolysis experiment is H2O will give us H2 plus O2, both in the form of gas, and our word equation will be water will give us hydrogen gas and oxygen gas. So, with electrolysis, it can be used to electroplate metals. In the previous experiment of copper chloride, carbon electrodes were coated in an even layer of pure copper. We say that the carbon electrode was electroplated with copper. One of the most important uses of electrolysis is electroplating. What electroplating is, it is a process where an electric current is used to break up a compound into metal particles to form a thin coherent metal coating an electrode. An example we can see this is chrome mags that are found on cars or chrome taps in your bathroom or in the kitchen. As you can see in the diagram over here, one metal gets broken down to be coated onto another metal. This process is known as electroplating. Thank you for coming to my lesson. We will see you for the next one.